This is the Peugeot 208 GT line, the current version. It does something that few hatchbacks do, and that's break the 0.3 drag coefficient barrier. For example, a few weeks ago, we showed how the Volkswagen Golf GTI had a drag coefficient of 0.33, which is pretty standard for a performance hatchback. The Peugeot though comes in at 0.29, over 10% better. In this video, we'll go through how it achieves that. So we simulated it at 20 meters per second. Let's go through the general aerodynamics first to see how the 208 directs the flow over its major features. To begin with, the 208 isn't actually very good. The front is very blocky from this angle, which means that we do have a lot of flow deceleration, and as we can see here by the very blue flow, that indicates slower flow, and we also get very high pressure as well, shown by this red coloring. So this is a major drag producing region. The reason why Peugeot made this front so blocky from an engineering point of view is for cooling and engine flow, so perhaps they couldn't reduce its size because of that need. But underneath, it suffers from the same problem that most cars suffer from. It has a sharp lip, which makes the flow separate over it a little, and this problem is amplified by the blunt front, which forces so much air downwards. You can really see how vertical that flow is traveling over the lip. We saw the exact same thing with the Nissan 370Z last week, but here it's even worse because of how much blunter the front is. Now, in a strange way, this region actually shows Peugeot's dedication to good aerodynamics, because if you look underneath, the front is sloped up a little bit. This could be for ground clearance, but I think Peugeot also sloped the front up like this to help a little with aerodynamics. By sloping it up like that, you reduce the amount of separation you get underneath. The technical reason is that the angle at the front is not as sharp now, and so it's easier for the flow to reattach. We do get decent low pressure underneath, which is good for downforce, and that's good for the 208 because it's a front wheel drive car. So the additional downforce around the front wheels increases its grip, but that comes with additional drag too, as we can see here in this drag orbit with all this red forming. While Peugeot kind of dropped the ball with the lower half part of the front, its top is really good. I'm really impressed with how little the flow accelerates over the front, because usually with cars there are two issues that this region faces. The first is if you make the front sharp and not curved, you risk having the flow from the front traveling over it and separating. That creates a large wake at the front and more drag. To stop that from happening, aerodynamicists migrated to rounding the front so that the flow could travel over it nicely without separating. That approach, however, leads to another problem. The flow accelerates like crazy. That then drops the pressure, and that lower pressure means there's less downforce, and particularly over the front wheels, which isn't good either. The 208 here is better though. It still has the very curved front, which means there's less drag, but you can see that the flow doesn't accelerate very much. Most of the flow stays fairly orange, which means it's around 25 meters per second or so. That is faster than the freestream flow of about 20 meters per second, but it's much better than most cars still. And that translates into the pressure, where we see in this pressure plot, we do get low pressure over the front, the blue region, but it's better than it could be. How did Peugeot achieve this? I think it's mostly because of how far upstream the curvature starts. If we look at this black section, that is arguably the start of the hood now, because you can see how it's already curving and then it blends straight into the conventional hood. So the curvature of the hood is spread out over a much larger length. That means that the flow doesn't have to accelerate as much or as quickly. And in aerodynamics, anytime you do that, you pretty much reduce the drag, because the slower the flow changes, generally the less energy is lost to viscosity. That's because you don't have as much mixing of different flow velocities, so the shearing forces are lower. So Peugeot did a good job here. These simulations were done with OpenFoam, and if you're interested in learning OpenFoam, then check out our courses here. In this plane, the underbody and top of the car are fairly normal. There isn't anything special really going on. Perhaps only the improvement over typical hatchbacks is the curvature over the top of the car isn't limited to just the roof, but the windshield is also curved and blends into the roof very well. That helps reduce pressure gradients. So looking at the pressure plot in this plane, you can see that from about halfway up the windshield, the pressure drops and becomes negative. From here it stays negative over the entire roof and doesn't change too much. There are some minor changes only. That is also good from a drag point of view for a couple of reasons. The first is what we were discussing earlier, where the less you mess with the flow, the less viscosity will sap energy away. The second reason why this fairly uniform pressure distribution is good for reducing drag is because of the rear. I know it's a little complicated, but I'll try to break it down into simple terms. The rear of the car is the greatest drag producer, and even more so for hatchbacks. They have very large rear faces, and those faces are exposed to low pressure, as we see here too, with this blue flow. That means you have low pressure on the rear face, and because you have higher pressure on upstream faces, that creates a force backwards, drag. So reducing the drag of the rear is a major challenge and focus. For regular cars, as you travel over the roof, the pressure increases. The more it increases, the more it pushes back onto the oncoming flow and decelerates it. That makes the boundary layer much thicker, and not in a good way. The thicker boundary layer means the flow near the surface has less energy, so when the flow enters the wake created by the car, it can't impact it as much. Here, Peugeot really improved this problem area, coming back to the pressure distribution over the roof, because it is more uniform than a typical car. When we look at the velocity field, the boundary layer is tiny. The green and blue flow close to the surface only extends up a few centimeters. This is way better than most other cars out there. As a result, this flow has more energy to penetrate the wake and feed it with higher energy and reduce the drag. The rear spoiler is helping that process too. You can see how it helps direct the flow along a particular path, and that reduces the wake size. If we look at the drag orbit, you can see that over the rear window, the drag produced is very low, impressively low. We'll cover more about that later. Let's quickly look at the underneath of the car at the back. We can see there is almost no diffuser. I guess there's a slight one considering that the underneath slants up a little, and then there's a sharp lip at the end, but it's pretty minuscule. This is a region that I think Peugeot could improve. As it stands, the floor is shot up a little, but not that much, and in the drag orbit, we get quite a lot of drag low down. A better diffuser would help that a lot. Overall, Peugeot has done a great job with reducing the drag of this car, and it actually makes sense because back in the early 2010s, Peugeot made a huge push to improve their car's aerodynamics. They jumped from being at the back of the pack to being a leader now, and they don't get any credit for it at all. Let's now look at the finer details around the car. First is the front wheel spoiler. This cut plane slices 60 centimeters to the left of the center line. If we look just ahead of the front left wheel, we see this plane coming down. It's a very basic wheel spoiler, but it really changes the flow. The most obvious effect is that it directs the flow downwards, so there's less flow directly hitting the tire. We also get a large wake behind it. While this might not seem like it's doing anything good, because what's the difference whether the flow hits this very flat face compared to the flat face of the tire, it's actually having a positive effect on the wheel. Looking at this cut plane, which is now a 30 centimeter horizontal slice off the ground, look at how little wake is coming off the front wheel. There's almost nothing. That's happening because the wheel spoiler is reducing how much of the flow is hitting the tire and flowing around it, as well as how much air is going into the wheelhouse and then has to pop out somewhere else. So the wheel spoiler reduces the wake and drag around the wheel. That's the direct effect of the spoiler, but it has another interesting effect as well if we look upstream. Ahead of the spoiler is the front of the car. Remember how this lip is very sharp, and that caused a surprisingly large wake and drag from it. In this off-center plane, there is a good chance that we'll still see some wake too here, but we don't actually. Why? Why did we get a wake off the lip in the center plane, but no wake here? It's partly to do with this wheel spoiler actually, because you now have flow crashing into it, and there's this hold up. It's kind of like having too many people trying to go through the doorway at the same time. There is this back pressure that pushes back on the flow upstream, so that forces the air to either go to the side or downwards, or some combination of both. Here we see that the flow is angled down a little more now, so even though the undersurface isn't angled that much, the flow is angled quite a lot. That allows this flow to use the rest of the flow that's close to the surface like a virtual surface. That's cool. Let's go back to this horizontal plane 30 centimeters high because we saw how good the wake was from the front wheel, but the rear wheel is equally impressive. And it might even be more impressive considering that you have the small wake from the front wheel flowing right into it, but the rear wheel wake is still really good. You can see behind the rear wheel that there isn't too much wake. I think it is largely to do with how the rear edge of the car curves in. It curves in a lot, and that means there's more room for the wake of the wheel to flow in and masquerade as just part of the rear wheel's wake. But let's not get fooled. Let's understand that while this rear wheel wake is very small, it's not that small. Because the rear is so curved, the wake is very small, and that's why in this drag orbit, we do get drag here, but there aren't too many red regions. If we move up to 50 centimeters high, the wheel's wakes are actually a little larger now, but the front wheel wake is occurring for a different reason to the rear wheel wake. The front wheel wake is occurring because flow from inside the wheelhouse is escaping right here. and it's being encouraged to do that by the low pressure we're getting around the front edge of the car. We get that low pressure because of just how curved the front is. It's very good for reducing how much flow is crashing right into the front and dumping its energy into the car, but that comes with a larger front wheel wake too, and drag. The wake from the rear wheel is just a generic wake, and if we look at this vertical plane slicing through the wheel, we can see that the bottom half of the wheel is producing a wake, and that flows right into the tiny diffuser. That creates an even larger wake around the rear, and that is partly what we're seeing in this horizontal plane. The rear bottom of the Peugeot isn't working as well because it has bad flow to work with to begin with, so the wake becomes larger too. We have one more horizontal plane which slices just through below the rear spoiler to see how it performs. It's performing in a very expected manner where the flow separates very cleanly off the little plates coming down. Those plates really stabilize the wake and can reduce the drag. And given how wide the rear is, the wake is actually quite narrow. Contrasting this to the Volkswagen Golf we did a few weeks ago, that car had a very small wake around the top half of the car, and then a very large wake around the bottom half. And with all these factors, the Peugeot produced a drag coefficient of just 0.29, which is very good for a hatchback. It also produced 5.7 kilos of lift, which isn't great, but again, very good for a hatchback. That's how Peugeot managed to make this car break the 0.3 drag coefficient barrier. If you're staying on YouTube, YouTube thinks you'll like this video, so check it out. Peace out amigos.